So this is just asking for expected weekly profit from selling cars. Okay, so we know that the profit, well, let's worry about rescaling at the end. Let's first of all figure out how many cars we expect this guy to sell every week. And so you can do this with your calculator. All right, so you'd want to, just as a reminder, it's good to go through stuff like this. You want to set up a couple of lists, and the first one would have the number of hybrids that are sold. And I have not done this, so I'm going to plug these in real quick. 0, 1, 2, 3, 4, 5. And then the second is going to be the probability of each amount. 0.32, 0.28, 0.15, 0.11, 0.08, and 0.06. Now, when you run your stat calc, your one variable stats, as long as you have a frequency list, so make sure that whatever frequency where you put the probability, that's your frequency list, and it just gives it to you. So we would expect him to sell 1.53 cars. Okay, so expected value, I'm not writing yet. Expected value of this random variable, I'll call it X, is 1.53. And now that's not the answer. What we want is the profit that he would expect weekly. And now we can figure out, so if he buys for 21, sells for 24.5, that's 3,500 profit per car sold times a 1.53. And there you go. You can just multiply that together.
Wait, so you found the expected value by finding the averages of all the probabilities?
Yeah, the actual formula that it is it's the sum of the value of X times the probability of X. And so that would be 0 times 0.32 plus 0 times 1, or 1 times 0.28 plus these two multiplied together plus all the way. But we let the calculator do that because it will do it automatically with one variable stats. Though you might find it faster just to do it by hand because this is all it's asking you for. It doesn't care about the standard deviation of this. But anyways, the answer here is C. And that is, I never ended the poll. That was our most popular answer. How about that? That's good. There you go. You can see it real quick. Okay. Let me clear this. Now we get to look at our progress we've made, fellas, ladies and fellows. All right. We started at Lee's Ferry. We've been working our way metaphorically down this river. We made it all the way to one of the highlights of the canyon, Havasu. Okay, and there we are. Look at that beautiful scene. And let's see, can we see that? Let's see what this is going to be. It's a surprise. Look at that view. Isn't that a beauty? We made it this far. All right, and then we can look around other places, but whatever. That's the highlight. That's what you hike down here, rode down here for. All right, let's get out of this, go back to this. What? No. Gosh. Sorry, I don't know how to do things anymore. All right, so now we're looking at an activity. Here we go. A local engineering firm had to conduct a series of layoffs recently. They will lay off 10 people. The company has 180 employees that could be laid off. All are equally qualified, so the company decides to use a lottery system to be carried out by the manager to decide who will be laid off. The manager posts a list of the employees to be laid off. 5 employees are women and 5 are men. One of the women claims this is gender discrimination and starts a lawsuit against the company. The manager responds, how could there be gender discrimination when half of the employees laid off were female and half were male? What additional information do we need to know to evaluate this statement? What you got?
How many females and males there are, like a proportion?
Is that what you're going to say, Leo? Did he steal your thunder?
Yeah, he did. I thought he pointed at me.
Well, I pointed kind of right in the middle. So,
I was like about to get it out.
okay. So I split the difference and Eli took the lead on that. Let's see what kind of person he is there. All right. So yes, we need to know how many are female and how many are male. All right, otherwise we have no real basis to start this question. All right, so I will tell you those numbers. There are 60 females and there are 120 males. So now we have something to work with. So how can we investigate this gender discrimination claim? And let's start by designing a simulation. Well, you're gonna have to think about simulations again. I'm gonna let you guys just think about that real quick. And if there are any thoughts you have on how we can design a simulation, let me know. And hopefully when we run through this scenario, you're like, aha, that's how we do simulations, and I'm gonna remember that. So I can randomly generate any number. If there are 180 employees and I'm gonna lay off 10 people, I can randomly decide through a random number generator, assuming I've numbered off the employees. So since our question is females versus males being laid off, I'm going to number all the female employees 1 through 60. And so that'll be females, which means 61 through 180 will be males. And then I can do a random number generator on my calculator. Remember that you have to go to math, over to the probability menu, and then random integer, rand int, 1 to 180. So it looks like this, rand int 1 to 180. Now I could pick, I could say 10 right here as a third number, and that would give me 10 numbers. I just need to make sure I don't get the same number twice. So you can choose to include the 10 and hope you don't get repeats, or you can just, I'll erase it. I'm not gonna do it with the 10 at the end. This is just gonna give me one random number from 1 to 180, and I'll just remember if I've already gotten that number. If the number falls between 1 and 60, it's a female that's laid off. If it falls between 61 and 180, it's a male that's laid off.
You find the random number generator?
Math, you have to hit that math button, third from the top left. And then probability is on the far right. And once you're there, you'll see rand int. Yeah. Yes, the AP test is only in person. Yeah, I don't know the time on it either. It's normally afternoon. All right, because you can't skip that AP test. All right, here we go. I'm going to run through one example of this. So I've got random integer. Now you're not going to get the same stuff if you try to follow along. I got 30, so that's a female. The next one was 169. That's a male and a perfect square. This is 78. That's another male. This is 23. That's a female. That's 171. That's a male. 107. That's a male. I've gotten 6 so far. 142. That's a male. 179. I haven't had that yet. That's a male. So we're at 8. 148. I don't think I've seen that number yet. Last one, I got 145. So in this one trial, I got 2 females laid off and 8 males laid off. Okay, so what I want you guys to do is I want you to do this on your own a few times. If you understood that simulation, you can kind of keep track and we're going to keep track of how many females were laid off. All right, so keep that going. If you can do a few simulations, we're not going to tell you exactly how many you have to do, but since there's so few of us, if you get at least a few of them done, then we can record on the next page the dot plot. So I will go ahead and move us to the next page, and we can move it into proportions. So I got 2 females, which means 20%. So I'm just going to clear my screen real quick. So I'm going to put a dot right here, my first one, and you can just keep adding dots as you're going, and we'll just build this up to see how this falls. So through the simulation, you can see we're getting a nice distribution going. Really nothing up on the high end, but you would probably not expect to get that. On the low end, even down at no women laid off, that was only one outcome that way. Okay, so let's go ahead. We want to keep track of this real quick. So I'm just going to quickly count. Looks like we got 1 here, 5 here, 1, 2, 3, 4, 5, 6, 7, 8, 9 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8. Hope I counted that right. 1, 2, 3, 4, 5, 6, and then 2. So the total number of trials we had, that's 6, that's 15, 25, 33, 39, 41. We had 41 trials. And there we go. So 41 total trials. And of the trials, 6 of them, 8 of them were at 0.5 or higher. And the result here, of course, was in the scenario that we set up was that half of the people laid off were women. Was that gender discrimination? Now we can see in our simulation, we got 8 out of 41. All right, we can do that math real quick. 8 out of 41 gives us about a 0.195 probability that that would happen by random chance, because this was random chance, okay? So I'm gonna go ahead and clear this. We'll remember the 8 out of 41 right there, and we'll do that again in a second. So, no, what percent of the dots are, oh, sorry, I shouldn't have deleted it all yet, but that's okay, I can fix that. No. Anyways, so there were 8. There we go. I can do that now. So that's where we were. What percentage of the dots represent half or more females being laid off? And well, oh, that's what we calculated. I was thinking wrong when I saw that. Half or more, we did that. 0.195. So I could have just deleted it and moved forward. Oh, what a waste of time. Not a waste of time. It's just silly of me. So we already figured out the probability of this happening is 0.195. 8 out of 41. And we want to interpret this percentage in context. Anyone want to take a stab at what that percentage means in context? Yeah, go for it. No, it's not starting off very. Okay, you try it.
Okay. 19.5% of the time, there will be more than half of the females, or more than half the people fired will be females.
There you go, half or more of the people. There you go. So that's pretty good. I don't know if you heard that Eli said, 19.5% of the time, half or more of the people laid off will be female. And we could also say something to the effect, what was I about to say? Something to the effect like the probability of half or more of the people laid off being female due to random chance alone is 19.5%. Does that make sense what I just said? Okay. Right, right. And so now that, and I'm glad you're thinking of that, but this is where we're going to have to kind of interpret if this is gender discrimination. All right. And we're going to get into that, but I'm glad you're already kind of thinking, trying to answer the question. So this percentage right now doesn't answer the question if it's discrimination or not. This is just the facts based on the data that we've gathered. No, we're not doing Z-score. We're going to do something different, something that you've learned about or you've heard about in the past, and now you get to learn what it's all about. Do we have convincing evidence of gender discrimination? Yeah. 90.5% sexist. So I'm seeing like no real definitive. Yes, I saw head shaking no. And again, right now, I don't know if anyone at home has any thoughts on this. Okay. I might jump in real quick and say, as of now, we might not have enough to really be sure what we would say to this. All right. So now we need to jump into hypothesis testing. So maybe in your head, you say there's a 20% chance that this would happen randomly. And that seems like a high probability. So this 50-50 split that happened, it could have just happened randomly, right? There's a 20% chance that it would. So if everyone understands the context and understands what that 20% represents, we just randomly laid people off. Laying people off, that's the nicer way of saying it. You randomly fired people, and 20% of the time, it was half women or more. And so maybe you're like, a 20% chance doesn't seem that unusual. So the hypothesis that we're testing, when we talk about hypothesis testing, the hypothesis is that the firing practices were biased in some way. Of course, we don't just decide on our own, we have to use statistics and figure it out. And so we're figuring out the probability of an observed outcome happening. And we're using that probability to determine if it was a result of random chance or if there's a real difference from what might be expected. And so to put it back in context, was the firing due to random chance, a real random lottery, or was there discrimination? And again, we don't have a clear answer yet, but we'll come back to it. So I'm going to throw out some concepts today that won't necessarily make sense right away because we're not doing this in the context of a problem, but it will make sense once we have some problems. When we're hypothesis testing, we always start with the idea that there is no difference between what we got and what we'd expect, okay? There's no difference between the expected outcome. So we're going to start with the idea that the proportion of fired people who are women is 33%, right? Because there are 33% of them are women. So we would expect 33% of the people fired to be women. The starting assumption that the outcome was a result of a situation that corresponds to the expected probability. That I don't even understand what I typed there. I'm sorry. But the idea that there's nothing going on, there's no nothing besides random chance happening, that's the null hypothesis. Okay? Again, it's a little bit weird to try and describe the null hypothesis right now, but we're going to put this back into context, and before very long, it will make a lot of sense. So here's maybe a practical way of looking at it. The null hypothesis is that there's no effect from any specific causes, in this case of discrimination. The alternative hypothesis is what we're going to propose as a result. Alternative hypothesis is that there is some kind of difference between what was observed and what we'd expect. So our alternative hypothesis was that discrimination was taking place and management was laying off women at a higher than expected rate. So we should be careful to describe how the observed outcome will differ from the expected outcome. And what that means is, in our particular example, we would say that if there's discrimination happening, that women should be fired at a higher than expected amount. And I'm going to pause right here. Well, I'll pause maybe at the end of this. We could also claim that a proportion will be lower than expected depending on the situation. And we're going to get into this more, but if we're not sure, we could just say that the observed outcome will not equal the expected outcome. This might seem a little bit abstract currently. Are there questions right now that you have that you'd like to ask? Okay. So when we do hypothesis testing, we're always testing the null hypothesis. And when this is over, we will either reject the null hypothesis or fail to reject the null hypothesis. Those are the only outcomes. This is something that I'll just keep reiterating this point, and you will, definitely understand this idea. So what you never say is that we accept the alternative hypothesis or accept the null hypothesis. You either reject the null or fail to reject the null. Because in both of these cases, we are just saying the data says that we rejected it or we failed to reject it. This almost is saying this is true. I accept the alternative hypothesis. We're never saying something is true. We're just saying statistically, we cannot reject the null hypothesis. Okay, so we're going to write our hypotheses in these ways. Sorry, our null hypothesis, and notice the notation. I kind of skipped over that before, but H hypothesis and then sub 0. So or H sub naught right here is the proportion is 0.333, because we would say, 33% of the people fired will be women. And then the alternative hypothesis is that the proportion that is actually higher than 33% because of discrimination. So equals is always the null hypothesis. And again, right now, I'm kind of trying to throw out the concepts, which might not completely gel together and make 100% sense. But as we start doing the full process of here's your scenario, let's set up our hypotheses, let's run through the analysis, let's interpret the analysis, it will all kind of fall into place. So I apologize if it's a little bit backwards how we do this. The p-value is the probability of obtaining a value as extreme as the observed one, or more extreme, on the condition that the null hypothesis is true. So let's hopefully try and tie this together. The p-value is something that you're probably at least familiar with, in the sense that you've heard about p-values in statistics. Maybe you have, maybe you haven't. And it's important to understand what a p-value means. In our specific example, this means that the p-value is the probability of having a proportion of women among those laid off of 50% or more greater, given that women are laid off at a rate of 33%. If there really was a fair lottery process, there'd be about a 33% chance of women being laid off. Is 50% an outrageous outcome given that scenario? So the p-value represents the area under the normal curve. So let me kind of diagram this out, because we will always be showing this on a curve. In this example, we would say 33% is the likely outcome. If we did this over and over and over again, we actually saw this in our scenario. 33% is the most likely outcome. 50% lives somewhere over here. And 50% or more extreme represents this area. Is this outcome of 50% or more unusual enough that we would call this a result of bias? Or is it common enough that we would say it's probably random chance? Is that making a little bit of sense? Okay. And now we know that this area right here, well, this is not the true area, but based on our simulation, is 0.195. All right, now we need to determine if 20% means anything. So this is where it all comes together a little, mostly. How do we decide if a change is significant or not? And the answer to that is we need to decide before we even begin what significance means for us. We have to decide how unusual an outcome should be before we decide that it can't be explained by random chance. And in this particular situation, is there a particular probability? Like, let's say, oh, that could only happen 1 in a million times. Would that seem highly unusual to you to get that result if it only happens 1 in a million times? Yeah, we would say there was probably discrimination. But if I say, oh, it's a toss-up, 50-50, and it happens, would you say that that was because of bias? Yeah, it's random chance. I mean, obviously. Or it seems obvious, hopefully. So somewhere in between 1 in a million and 50-50 chance, there's a point where we decide, here's our cutoff point. This is where it's too unusual and we don't think it was random. And here, anything short of that, we decide it is random. So is that making sense?
Yep.
All right. Does anyone have a thought right now about where they'd put that? Like 1 in a million is a really low probability. Is 1% your cutoff? Is a 10% chance your cutoff? Is a
3%.
30%?
3%.
3%. Okay. Anyone have a different idea right now? Just put a visual on this. Here's your 50-50 chance, and we decided that's not, that's not significant because 50-50 is a toss-up. And maybe way over here, and I'm, this small little area moving off to the right, maybe that's your 1 in a million chance. And we decide that's highly, highly unusual. So I'm not looking for a Z-score. I heard 3%. I don't know if anyone else has a thought, but maybe you're thinking in your head, you have a particular cutoff point where you're like, that's too unusual. And so therefore, I think it's a result of some kind of a bias. It is an arbitrary, this level that we decide is called the significance level, and that is arbitrarily set where we decide it's unlikely enough for us to reject that the null hypothesis is true. In this case, the null hypothesis is that women really are laid off at a 33% rate. We can reject that if it's too unusual, the result that we got. All right, so let's kind of put this, here is where we frequently put significant levels between, or it's typically 0.05, that's the most common one, or a 1%. And we call these alpha levels. And there you can see the Greek letter alpha also written like that. So we needed, so a 0.01 significance level means that if it happens less than 1 in 100 times, then we decide it's unlikely to occur by chance. So if we pretended that 9 women were laid off instead of 5, the probability of that happening is that right there. So right here, this would be pretty darn convincing. If there were 9 women laid off and there's only a 400ths of a percent chance that could even happen, then that would be pretty convincing to me and probably to everyone that it was an unfair process and they were discriminating. All right. So, and to maybe to wrap it up, since we got 19%, 0.195, 20%, whatever we want to call it, because we got this, maybe here's where we say, well, it's not a low enough probability of happening for us to consider it statistically significant. Therefore, we fail to reject the null hypothesis. And our result for this might say, you know what? It wasn't discrimination. It was random chance. And according statistically, it seems like it was random chance. And so no statistical basis for having a lawsuit.
I thought that was acceptable.
We never, there you go.
What do we do when we accept it?
You fail to reject. Leo paid attention to something. Okay. So in this case, we fail to reject the null hypothesis, and we interpret it from there. We're not going to jump into the whole process today. It's basically just to kind of introduce some concepts. And hopefully you're following along with the concepts, at least on a broad level, clearly enough. So here we've got the scenario for this, for our practice. Calcium is a vital nutrient for healthy bones and teeth. There you go, you learned something today. All right. The National Institutes of Health recommends a calcium intake of 1,300 milligrams per day for teenagers. The NIH is concerned that teenagers are not getting enough calcium on average. Is this true? We are not going to do a full hypothesis test on this We are just going to answer a few questions. We want to create some appropriate hypotheses for performing a significance test, being sure to define the parameter of interest. Okay. So let's figure out the parameter of interest first of all. What are we trying to estimate? This is an inference test, I should say. So just like we were inferring about population when we were doing confidence intervals, we are inferring about the population based on this. So what is this, are we dealing with proportions or means? Looks like means in this case, because we're talking about, does the average teenager get 1,300 milligrams per day of calcium? So we are dealing with means, and what we are saying is, in this particular case, this is the true mean daily intake, if I can write, daily intake of calcium for teenagers, and I'll put in milligrams, whatever. So that's what we are going to draw an inference on. And now we want to create a null hypothesis, which is H sub naught, and the alternative hypothesis, which is H sub A. You can write that as H sub 1, but H sub A is the more common way of doing that. So our null hypothesis, remember, the null is always equal. And the parameter here is the true mean. So we're saying that the true mean equals what? 1,300. So again, null hypothesis, we would say teens really are getting the correct amount of calcium every day, and there's nothing weird going on. What would our null hypothesis be for this particular problem? Wait, this is our null hypothesis. What is our alternate hypothesis? I don't know what I just said. I'm sorry. What is our alternate hypothesis for this particular situation? Less than 1,300. So there you go. So you're saying it kind of in a phrase, and now we're putting in math terms. Yeah. So that teens really are getting less than 1,300 milligrams. Okay. Those look like appropriate hypotheses to test. Okay. And maybe just to conceptually run through this, let me actually see something right here. So we're going to test this hypothesis. Okay, so I don't need to come up with a scenario. We're going to keep going. They ask a random sample of 20 teens to record their food and drink consumption for one day. The researchers then compute the calcium intake for each student. The data analysis reveals that the sample mean from this group is 1,198 milligrams, and the standard deviation is 411. Researchers performed the significance test and obtained a p-value of 0.1404. Okay. Explain what it would mean for the null hypothesis to be true in this setting. I will say this is not like a typical AP question, and this would be more like a multiple choice question where it would give you a number of options.
Would you say something like the mean for this sample isn't unusual, or like, I don't know what words.
Yeah, I hear what you're going for, and I think that that's a fair way of approaching it. I think quite literally with this, maybe the answer that they're looking for here, and this is, you know, this might drive you insane with statistics stuff, because it can drive me insane too, because, you know, it's not like completely clear, like, wait, what are they asking me to do? So here's my interpretation. What would it mean for the null hypothesis to be true? What it means is that teenagers really get 1,300 milligrams of calcium per day. That's what it would mean. The null hypothesis is true. Okay? Now, this is where we jump into the numbers a little bit with the next one. Interpret the p-value. So the p-value is 0.1404. And let me go ahead and interpret this one for you. I'm not going to ask you to try and do that. So here's what the p-value means. It means if teenagers, I might write this down, okay? If teens really do get 1,300 milligrams of calcium per day, then there is a 14.04% chance or probability of obtaining this sample result by random chance alone. So to phrase this a little differently, this is kind of a very straightforward way of saying it. But let's pretend that on average, teens really do get 1,300. And this sample of 20, which is not a huge sample, we just happen to get people who get less than that every day, right? And I picked people who had like 1,000 milligrams of calcium this particular day, maybe 800, and someone had 1,700, but it all averages out to basically 1,200. So it just happens to be, I picked some people on average who get a lower amount. But I could have taken another sample and it was higher than average, right? So the probability that just randomly I'm going to pick 20 people and it averages out this way is 14%. Is that, well, we can answer the next question now. What conclusion would we make at the alpha level or significance level of 0.05? Do we reject or fail to reject the null hypothesis? We fail to reject the null hypothesis. Okay, so we can say something to this effect. Because our p-value of 0.1404 was greater than alpha 0.05, we fail to reject the null hypothesis. And you could write out null hypothesis, you could put H sub naught. All right. And we could add another, because that doesn't put any context onto it. So we can add some context. There is not convincing evidence. There is evidence, but it's not convincing evidence. There is not convincing evidence that teens don't get enough calcium. All right. So, are there questions on just this interpretation right here? All right. So here we go. Before I log you off, there's been a stop sharing real quick. I found this a while ago, but we haven't been learning about null hypotheses yet. So now I finally have you. And I've been saving this picture for so long. All right. So now that you know what a null hypothesis is, here we go. You can give this to your love next Valentine's. That's romance right there. Me?
Video shows me all the-
I won't lie. I used to have my hair in that haircut. And I swear, every time I look at this, I'm like, I think it's a picture of me when I was that age. Actually, as a little, oh, there we go. You can see Leo's screenshot right now. Okay, so anyways, I can stop sharing that. Let me go back to your homework real, well, you don't need to see your homework. It's on the Canvas page, but I'll share it anyways because I'm just a good guy. What can I say? All right. So there it is. We got some conceptual understanding today, and I don't think the worksheet is active right now, but it will be in the next few minutes. So have a wonderful day. If you have any questions on anything, stick around. Otherwise, you can go and party on.
Thanks, Mr. Davis.
Thank you.